Here we want to find the angular momentum of a thin spherical shell with a given mass and radius that's rotating about an axis passing through the center of mass with a given angular velocity. We are asked to find the angular momentum of a thin spherical shell, which is a rigid body, meaning it's an extended object, it's not just a particle. And so we have an equation for that we can use. We said that the angular momentum is I times omega. That parallels the equation that we have for linear momentum, right? Linear momentum and angular momentum are analogs of one another. Mass and moment of inertia are analogs, and velocity and angular velocity are analogs as well. So if we want to find the angular momentum, that means we need to know the moment of inertia of this thin spherical shell about an axis passing through the center, and we need to know the angular velocity. The way that we would find the moment of inertia would be from a table. We can look at this table from the book. We can look for a thin spherical shell about a axis that passes through the center, and we can see that the moment of inertia here is going to be 2/3 mr squared. We know m and we know r, so we'll be able to find the moment of inertia. The angular velocity is measured in radians per second, so this is an angular velocity here. What we are kind of imagining here, since we're not really given a specific direction, we can kind of imagine this thin spherical shell rotating in space. Since we're not really given a direction, we can imagine that the axis of rotation passes through the middle. And we can imagine that the angular velocity vector is maybe aligned with the z-axis, meaning that the whole sphere is rotating in the xy plane. And then in that situation, we would think that the angular momentum vector would be pointing in the same direction. So since that hasn't been made very clear to us here, what specific direction it is, we can just imagine that this thin spherical shell is spinning in space, and we can line up our axes so that the axis of rotation aligns with the z-axis for the sake of simplicity. We can put all of that together and say that the magnitude of the angular momentum is the moment of inertia times the magnitude of the angular velocity. We have the mass of the sphere and its radius. We also know the angular velocity. And we can put all of that together to find the overall angular momentum. In this case, again, we'll use significant figures, and we'll round this to 140 kilogram meters squared per second is the magnitude of the angular momentum. The direction is in the same direction as the angular velocity. Let's say it's along the z-axis since we don't have any other information in that regard.